So as we begin our first section of Module 11, or Section 11.1 here, we're going to take a look at our root locus plots. So we're going to go through a couple different examples, how we can draw these out by hand, how we can interpret them and utilize them when we're designing our systems. So the first thing that we want to focus on here is, what is a root locus plot? Well, this is a plot of the location of the characteristic roots as a parameter value is varied. So we'll go through a couple different examples of how we can vary different parameters within that to double check how we can optimize our system. So these are basically going to be an overview of how the response is going to change if whatever parameter value we're varying is changed. So we might want to have a whole set of K values, spring constant values, that we want to see, okay, which is going to be optimal here for our system as we're designing it. So we want to run through this and use these plots in order to help us do that optimization. So these plots were around and available long before the computer systems were, so we didn't have resources such as MATLAB at the time. So I'll go through how to draw these out by hand at first, and then as they get more complicated in higher order, how we can utilize MATLAB to quickly generate these rather than doing it by hand. But I think it's beneficial so we can understand how these work and how these can benefit us if we go through how we can develop them by hand and how we can interpret them on our own before we just plug it in as a command in MATLAB. So in order to do this, we'll take a look at some of these more simple second order system plots that we can do by hand just to illustrate the concept. And once we feel comfortable with that, we can move on as we get towards the end of this module and do some higher order systems and see how we can utilize MATLAB and Simulink in order to do these as well. So let's take a look at a relatively simple example here. We have a characteristic equation given by the general form here that we have our ms squared plus cs plus k is equal to 0. So we talked about wanting to vary one of the parameters here. So in this case here, let's just start off by varying our spring constant k. So we want to consider what's going to happen when we vary that there with the damping constant c and our mass m. So how is varying this k from certain values, maybe from 0 to some maximum value here, going to affect the system as a whole? Now with this here, what we're going to do to simplify this down a little bit is we're going to give set numeric values. We're going to say we know the mass and we know our damping constant here. So our mass is given as 2 and our damping constant is given as 8 here. So we want to see what's going to happen now if we want to vary our k values. So the way that we're going to do this is we're going to take a look at the display of our root locations as that k varies. So before we begin too far into the solution here, what we want to do is take that information that they tell us here, that we know our m is equal to 2 and we know our c is equal to 8. We're going to plug them into this general characteristic equation up here. So there's our m right there, and there's our c there. So plug in our mass and our damping constant c. So this now becomes 2s squared because our mass is equal to 2, plus our 8s because our c here for our damping constant is equal to 8, plus our k. And we're going to leave this as k because this is going to be what we're going to vary here when we're trying to determine these root locations. And this is equal to 0. So this is now our new characteristic equation. So this is a pretty simplistic characteristic equation here. And if we want to find the roots of a quadratic function like this, we can use our quadratic formula here. So it's relatively straightforward. We have our general equation here. The x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And we know our a is equal to 2, our b is equal to 8, and our c is equal to k. So we can plug those all in there. Everywhere there's a b, we plug in our value of 8. So we have a negative 8 plus or minus the square root of 8 squared minus 4a, where a is our 2 value right there, times c, which is our k value there, all over 2a, which again is our 2 value right there. We can reduce and simplify this. 8 squared is 64. And we have that 4 times 2 is 8 here, and 2 times 2 is 4. So now we have this equation for x. X is equal to 8 plus or minus, so there's our two roots right there, the square root of 64 minus 8k over 4. So what we want to do when we vary our k is, as we're solving for these roots from this quadratic equation, is we have a range of values for k that we want to plug into this equation here and solve them out. So we can do this by hand for a simplistic one like this, depending on how many k values we want to evaluate and the difference between each of the k values, the interval we want to go with for our different k values there as we plug it in. So for this equation here, we take a look at some of the general rules that we're seeing for our roots here as we plug in different values for k. So if our k is greater than 8, the roots are going to, if the k is less than 8, our roots are going to be real and distinct. If k is equal to 8, they're going to be repeated. And if k is greater than 8, then we're going to have some complex numbers that we're going to have to deal with our roots. So now that we have this quadratic equation here for our roots, we can see again x is equal to -8 plus or minus the square root of 64 minus 8k over 4. We're going to evaluate this for values of k where k is greater than or equal to 0. So what we're going to see is the plot, so we can see below here A and B here. So let's focus first on part A. And this is going to be the plots of the roots of that equation, our general equation that we saw before, our characteristic equation, with our mass M and our or our damper value here, C, plugged in. So M was equal to 2 and C was equal to 8. And our spring constant is going to vary here for values of K greater than or equal to 0. So the roots for this we can plot here as K varies through various positive values. So now we can see on the left, on part A over here, we can plot the roots with these dots that we see here. So we have these dots on the equation here, we're going to plot them, and we can see our x-axis here is our real axis, and our y-axis here is going to be our imaginary axis. So as we get these values for x, as we vary our values of k, we can plot them as dots on this plot here, and shown in part A. Now, we're going to go through how we can actually do this by hand in a minute here, and I'll do this problem out by hand, and I'll also go through and show you how we can solve the quadratic equation using Excel as well. And I know we've primarily focused a lot on MATLAB, but for a problem that's this simple, maybe we want to double check our quadratic here and set up a little macro or a system of equations within Excel so we can solve this and vary our values for k. So rather than doing it out for a different value of k by hand every time or plugging into our calculator every time for different values of k, we want a little bit more systematic approach here so we can set up a values for k here within Excel, and I'll go through how we can do that. One thing to note here, as we look at our plot, there's a lot of information we can determine from these roots, the plot of the roots here. And one thing that we can see here is for k less than 8, the dominant roots are going to lie between an s value of 0 and -2. So we'll be able to infer a lot of things from these plots once we plug in for all of our values of k. So the next thing that we can talk about here is once we see how this acts in part A, we note that the general trend of these dots, we can then connect these with solid lines here so we can see we have something a little bit more simplistic that we see over here by connecting those dots. So the first thing that I do here in this plot here is I utilize Excel, and I utilize this relationship here. So I have this solution here where I can say some cell C3, so I can look over here. There's my cell C, which is my B. So negative B plus or minus. So I'll have two sets of this equation, a plus equation and a minus equation here, which I'm going to call result 1 and result 2 down here in my table. The square root of my B value squared, which again, B corresponds with column number C here, minus 4. Then we have B3 and D3, which are simply A and C when I correspond to my quadratic equation here, all divided by 2 over my column B3 here, which is my A values here. So I've come up with a quadratic equation based upon the problem, the characteristic equation they gave us in the problem here, and I can get my two roots from this, which are the plus and the minus here from my quadratic equation. Now, the thing that I notice is if I go down to the bottom here, I can see that once we get above a value here of 8, all of a sudden I'm starting to get errors. So based upon how I've written out this equation in Excel, I can't deal with my complex numbers. My imaginary numbers here aren't going to be accurate. I'm just going to get an error message down here. So what I want to do for this now is I want to be able to change this relationship, this equation here that I've put into Excel so that I can look at my real and imaginary parts of my roots. So in order to take into account the real and imaginary parts of some of the roots here, once we get past a k value of 8 here, what I do is I change my equation for solving the quadratic. And the way I do this now here is I'm going to look at the numerator and denominator separately, and I'm going to use the functions ISUM and IAMSUM and IAMSUB here within Excel in order to take a look at the top half, the numerator portion of the quadratic equation here, and to take into account our real and imaginary components that could comprise our roots for this here. So I rewrite our equation. So rather than 1 and 2 where I use my standard quadratic equation here, and now I couldn't take into account my imaginary portion of my roots here. I now deal with my numerator and denominator separately, and I now use this im sub and im sub functions here in order to take those into account. So I do that out here, and I calculate out, again, there's two roots, the plus and minus from our quadratic equation here, so I'm calling this the complex numerator minus portion, the complex numerator plus portion here, and then I divide the numerator by our denominator, which is 2 times a, from our quadratic equation over here, and that's how I come out with my results 1 and results 2, or my two roots for the equation now, that now you can see above 8 here, I now have values for my real and imaginary components. So I have -2 plus my I component, and I have -2 plus my I component over here, and the same thing here for when I have my value for my quadratic here for my k of 10. So for k equals 9 and k equals 10, I still now have values here that have a real and imaginary components. So I've also included this spreadsheet that I'll attach to Blackboard as well, so you guys can go through this and utilize this as a tool for you as well to see what these equations are, so you can solve some quadratic equations for various homework and exam problems utilizing this as well. So once I do that there and I get my results for that characteristic equation for my k values now going from 0, because again these are positive k values greater than or equal to 0, up through, and I only went up to 10, but we could keep going from there. I only went to 10 just because I wanted to go through and show you how we can plot this by hand and not plot this within Excel. So if we want to plot this by hand here, what I can say is, okay, for my k is equal to 0, I get my two root values, or my two poles, pole 1 and pole 2, of 0 and -4. So I come over here and I draw out my imaginary axis as my y-axis, my real axis as my x-axis here, and I say, okay, for k is equal to 0, I have a roots of 0 and -4. So there's my 0 root right there that I've drawn in red right there for k is equal to 0, and I have my k is equal to 0 here for the second root of -4, so I plot those in. Now I've only plotted out a couple of these just so we can kind of see what's going on. Then I'll jump over to k is equal to 3. When k is equal to 3, I have a pole at -0.4 and -3.58. So here is my -0.4, my -3.58 value there. Then I jump up my k equals 6, and I have a -1 and a -3 root there. So there's my k equals 6 at -1 and -3 there. So you can see this is symmetric, and it's going to be symmetric about here, where my k value here at k is equal to 8 is equal to -2 and 2. So my roots are equal there where k is equal to 8, so that's my root right there. And then from there you can see I start to have real and imaginary components. So I plot those out here on my imaginary axis here. So at -2 and my real axis, I have for k equals 9 a 0.7 and a -0.7. So there's my -0.7 and 0.7 on my imaginary axis. And for k is equal to 10, I have my -2 for my real component of it. So again, -2 right there, still following up and down that axis there. And I have my I, -1i and +1i there. So there's my positive I for k is equal to 10 and my -I for k is equal to 10 there. So we can keep going, and we'd see that these would keep going up there for our real and imaginary components as we increase past k is equal to 10 there. So what this plot shows is the roots of our characteristic equation for 2s squared plus 8s plus k values now as we vary our spring constant k through the positive values there and how those correspond. So now we can utilize this plot to say, okay, as my k values change, what is going to be optimal here for the k value for whatever our system is here. So this is for going through and varying our k value and having a set known mass and a set known c value here for damping. Now we could do something different, and we're going to go through examples doing just that, where we have a known value or a desired value for k, and then we go through and vary our c and our m, our mass values there, and again plot it back out and see how things go, and we can optimize our system based upon this plot. So just another example before we get into varying those there. Let's vary k here. So we have the locations of poles for some function here as a function of k, where k goes from 0 up to 50 in this case here. And then we have our pole 1, our pole 2, which are our two roots. So again, we have our imaginary axis on the y, our real axis here on the x, and we can go ahead here and we can see that, once we go above a k value of 25, where these are equal to each other here, right there, we then start to see our real and imaginary components come into play for k values higher than 5 there. But from 0 to 20 right here, or up to 25, we have our values here for our two different roots. So let's just take it 0 here. So k is equal to 0. We have a negative 10 and a 0. So k is equal to 0. There's a negative 10 and a 0 there. K is equal to 5. We have a negative 9.4, and we have a negative 0.53, so we can go there, and then we so on and so forth, and we continue up until we get to our k is equal to 5, where it splits and goes and get our imaginary components as well. So just another example of how to take this information from solving our quadratic equation from our characteristic equation here, varying one of our variables here, which in this case is our spring constant k, and plotting out our root locus plot here, and using that to optimize our system. So now we've talked about varying our k, let's talk about varying our damping constant, our c value here. So we still have the same characteristic equation here, our ms squared plus cs plus k is equal to 0. But now we're going to consider what happens when we vary our damping constant c and hold our mass constant as m equals 2 and our spring constant as k is equal to 8. So again, we want to display now on our plot here the root locations as our, in this case here, our c varies. And we want to display it there. So as our c varies there, we can plug back in to our characteristic equation here for our known. Our m is equal to 2, and our k is equal to 8. And our c is what we're going to be varying here. We plotted out the same way we did before that we showed for when our k varied. And what we end up with here is our plot that we show down here, which is showing the roots as of c varies for 2s squared plus cs plus 8 is equal to 0. And again, we're only varying our c from positive values here, so we can see what kind of happens with our graph down here for when we vary our c as compared to varying our k values. So now we've gone through and taken a look at our results and our roots as we vary our spring constant k and our damping constant c. So last, let's take a look at our mass. What happens if we vary the mass? What do our roots look like? What does our plot look like for that there? So we're going to start with our same characteristic equation here, our ms squared plus cs plus k is equal to 0. And we're going to plug into this here now for a known value for c and a known value for k, and we're going to vary our m here. So what happens as we vary the mass? So we plug in, let's say our k is equal to 6 and our c is equal to 8. So when we plug that in there, we end up with ms squared plus 8s plus 6. And now we're going to display the root locations as we vary our mass in positive values here. So for mass greater than or equal to 0, we can plug that in and solve for our quadratic equation for the different values for m, and plot those on our real and imaginary axis, where imaginary is on the y and our real is on our x here, the same that we've done for our varying our k and varying our c. We do the same thing now as we vary our m. Get those same roots, plot them on this axis here, and what we see now is we have the plot of the roots for ms squared plus 8s plus 6 is equal to 0 for values of varying m here, and we get this result shown here in this plot. So now that I've given you that Excel sheet for our k's varying, what I would encourage you to do is play around with that Excel sheet and now go through and set these values that we've done here in the last couple slides here for varying our mass and varying our c values with the set values for the other two. So go through, tweak that Excel spreadsheet and worksheet that I've given you, and see if you can come up with these same plots here by hand. So graph them all out, create that t-chart, come out and plot it just like I had in the previous slide for when we did it with varying k, but do it now for varying mass and varying c values there, and make sure that you can recreate these same plots the same as we've seen here. So that'd be a good practice exercise in order to learn how to do these plots by hand. So now what we want to do is figure out how to design using the information from the root locus plot. So we're going to illustrate how to use the information we see there from that root locus plot that we had from the previous 3 examples there as we varied our k, we varied our c, we varied our m, and how do we use that to design our control system? Take that information and tweak and optimize the control system. So the main thing to ask ourselves here is, what does that information tell us? So what it's doing is now that root locus plot is a plot of the location of these characteristic roots in terms of whatever system variable we're choosing to vary here. So again, could be the mass, could be the spring constant, could be the damping constant as well. So as we vary those, we're going to get information that is going to be our characteristic roots and the location of those characteristic roots. So each path on this plot is going to correspond to one root of the characteristic equation. As you can see, we had different characteristic equations as we varied different things within, different system parameters within that characteristic equation. So these paths are going to be referred to as our branches of our plot. So the purpose of this slide here is kind of a guideline for sketching the root locus here. So this is given a lot more detail in the textbook, but what I want to do is kind of summarize it quickly in a location you guys could reference back to and look at this as you're going through and starting to sketch these out. So one thing that we want to notice here is that this root locus plot is going to be symmetric about the real axis. And we noticed that there in all three examples when we took a look at our plots there and saw that it was symmetric. When we put each of those dots in there, it was symmetric about that real axis. And the reason this occurs here is because our complex roots only occur in conjugate pairs if the polynomial coefficients are real. So let's here consider this general root locus equation here. We have 1 plus kp of s is equal to 1 plus our n of s over d of s here is equal to 0. So this is saying that our k is equal to the product of the magnitudes of the vectors from poles to point S over the product of the magnitudes of vectors from zeros to point S there. So with this here, here's the guidelines is a summary as compared to the in detailed description from your textbook here. So we have the assumption here at the beginning that the order of ns is no greater than the order of our ds here. So our ns as a numerator, ds here as our denominator there. So then we'll go through each of these guides here. So guide 1 in summary basically tells us that the number of paths is equal to the number of poles. And that the paths are going to start at the poles of PS with our k value is equal to 0 because we're dealing with positive k values there. And they're going to terminate with a k is equal to infinity either at the zeros of PS or by leaving the plot. Guide 4 tells us that the root locus exists on the real axis only to the left of an odd number of real poles and or real zeros. And 5 lets us know where the locations of our breakaways are. So now we'll continue on from here and take a look at guides 6 through 10. So again, these are all just quick summaries as a place to reference back to in these slides here from our lecture slides rather than going through the in-depth details that are given in your textbook. But as you're looking at these, if you want more information for as you're sketching your plots out, some details, please reference back to the textbook for these. So we'll continue on with guides 6 through 7 as we're talking about sketching our root locus here. So 6 tells us that the paths do not terminate 0 and approach infinity along the asymptotes. Guide 7 tells us that the asymptotes are going to intersect the real axis at a common point. Guide 8 tells us that the points at which the paths cross the imaginary axis and the associated values of k can be found by substituting in this s is equal to j omega into our characteristic equation. Guide 9 talks about how to determine our angles of departure and angles of arrival. And guide 10, we start dealing with our polynomial equation. So these are the 10 different guides briefly summarized. And again, reference back to your textbook for the details for each of these. But as you're going through, a quick place to reference these as you're sketching out your root locus. Another great resource from our textbook here is this table here that talks about the sketching procedure here. So if you're dealing with each step individually here, so you have step 1, express the characteristic equation in standard form. So we saw how we did that there in our couple of example problems that we did. And it gives you a little bit of information and details over here for how to do that. Step 2, determine your poles and your zeros. Step 3 in the procedure, plot the poles with an X or a dot and the zeros with another reference there. In this case here, they're telling you to use an O. Use the same scale on both axes. And again, note here that the locus is going to be symmetric about our real axis that we saw in a couple examples as well. Step number 4 in our procedure here is to sketch the root locus on the real axis first, and then determine any breakaway or break-in points here in step 5. And if our P is greater than Z, compute the angles and the intersection points of our asymptotes there. So as we continue on here in this table for our procedure for sketching our root locus here, we can go to step 7, where we're in step 7, we're going to determine any crossover points. In step 8, we're determining any angles of departure from the complex poles and any angles of arrival from the complex zeros. And in step 9, we're determining the value of k at any desired root location. And lastly, we're going to locate our remaining roots corresponding to our case of D.